Okay. My topic today is about how accurately can quantitative imaging methods be ranked without ground truth, an upper bound on no gold standard evaluation. Here is the outline of this talk. Let us start with the background and motivation. To begin with, quantitative imaging is emerging as an important technique in the clinic. The basic idea is to extract numerical or statistical features from medical images and use that to help with clinical decision-making. It has been used in multiple different medical applications. Given the interest in quantitative imaging, different quantitative imaging methods have been developed. For clinical translation of these methods, it is important to evaluate them on the underlying quantitative task. Ideally, this evaluation needs to be conducted with patient data. However, with patient data, there are no gold standards to compare with. To address this challenge, no gold standard evaluation techniques have been developed. The basic idea is that although we don't know the true value, the measurements is the results of a specific image formation, image analysis, and a quantification process being applied on the true image. Thus, there should be some statistical relationship between the merit and the true value. The question is, can we explore this statistical relationship to estimate some figure of merit can be used to compare the quantitative performance of different methods? Let me make this idea more concrete. Let us consider three segmentation methods here. Let us consider three quantitative imaging methods here. The NGSE techniques assumes that the true and merit values are linearly related by a slope bias and a zero mean Gaussian distributed noise term. Now, if we have the true value, we can directly use the least squares technique to estimate these parameters. And then we can rank these methods based on these parameters. For example, if in these figures, method 2 has the smallest noise term, then it can be the most precise one. And method 1 has the largest noise term, it can be the least precise one. But the challenge is we don't have the true value. To address this challenge, current NGSE techniques assumes that the true values are sampled from a parametric distribution. With these assumptions, existing NGSE techniques can derive a maximum likelihood estimator to estimate these parameters. Now, after we estimated these parameters, we can actually use the bias and slope to calibrate the measurements. Then the noise term will be scaled by the reciprocal of the slope term. Thus, existing NGSE techniques are ranking the methods based on the using noise to slope ratio based on precision. The efficacy of these techniques has been demonstrated in evaluating different quantitative imaging methods in multiple different medical applications. Well, these techniques are very promising. There are still some very important questions that need to be answered. Now, let me phrase these questions in the context of evaluating different image segmentation methods on the task of quantifying metabolic tumor volume. First, now I have a set of segmentation methods that I want to evaluate, and I might wonder, for my current patient population size, how best can NGSE technique perform in ranking these methods? Since previous studies have shown that with the patient number decreases, the NGSE techniques will deteriorate. Thus, I might wonder, for my current patient population size, is it enough for the NGSE technique to yield accurate ranking, or do I need to collect more patient data? The second question is that for the segmentation methods that have inherently very similar noise to slope ratios, how accurately can NGSE techniques rank them? So, for example, here are the three segmentation methods I want to compare. It is very obvious that method 2 has the smallest noise to slope ratio, thus it is the most precise one. And method 1 has the largest noise to slope ratio, thus it is the least precise one. Let us say that for this case, NGSE technique can yield very accurate rankings. But I might consider, what if this is the set of segmentation methods that I want to compare? In this case, I might wonder, can NGSE technique still rank them very accurately? And the third question is that one might wonder, how does no-gold standard evaluation comparing to the evaluation with gold standard? Since we know that gathering gold standard data can take substantial efforts, time, and resources. For example, in comparing image segmentation methods on quantifying the metabolic tumor volume, the one potential gold standard is the resected tumor. It is hard or even impossible to gather all the resected tumors for a patient population. Or even we can get this kind of gold standard, we will still need to use statistical estimation techniques to estimate the figure of merit. There will still be inaccuracy. Thus, we might wonder, how does no-gold standard evaluation comparing to the evaluation with gold standard? If the difference between them can be acceptable, maybe it can save us from the time-consuming process of gathering gold standard data. No, actually, all these questions can lead to one central question. That is, how accurately can quantitative imaging methods be ranked without ground truth? Is there an upper bound on this accuracy? And the answer is yes. Now let me introduce the theory of this upper bound. I will first give some intuition here. As we have mentioned before, the NGSE techniques estimate the figure of merit, which is the noise-to-slope ratio here for each method. And since it's an estimation algorithm, thus we care about its accuracy and precision. And normally we will want the estimation to be unbiased. Thus consider if we are comparing three segmentation methods here, and if we plot the estimated noise-to-slope ratio for each method, it might be approximately like this. And from the overlap of the probability distributions, it is highly possible that the ranking of these three methods can be inaccurate. Can be inaccurate. But if the estimation is more precise, we see that the probability of inaccurate ranking will decrease. So while the minimum standard deviation of the estimation is given by the criminal bound, thus we can use the criminal bound to compute an upper bound on ranking the methods. To compute the criminal bound, we will first need to derive the log likelihood function. As we have mentioned before, existing NGSE techniques assumes that the true and merit values are linearly related by slope, bias, and a zero mean Gaussian distributed noise term. Thus, for the PIS patient, we can write the measurements given by the K methods and the relationship between the measurements and the true value using this equation. Since these techniques further assume that the true values are independently sampled from a parametric distribution. Thus, we can write the log likelihood function using this equation. With this log likelihood function, we are able to compute the facial information matrix, which will further yield the criminal bound for all the parameters. As we recall that the figure of merit in used to rank the methods in no-gold standard evaluation is the noise-to-slope ratio. Thus, the figure of merits are computed as a function of all these parameters. If we denote the Jacobian matrix of this function as J, then the criminal bound for all the NSR values will be this equation, will be computed using this equation. Thus, when the unbiased estimate achieves the criminal bound, the estimate can be approximately Gaussian distributed, with the mean given by the true value and the covariance matrix given by the criminal bound. With this distribution in mind, we can actually compute the probability for correctly ranking the methods. For example, now we have the true NSR values having this kind of order. We can compute the probability for correctly ranking the methods using this equation, and also the probability for correctly identifying the most precise method using this equation. These are actually just the integration of a Gaussian distribution under linear constraints. now we have all this framework for computing the upper bound of correctly ranking the methods. We can use it to answer all the questions we have before. In this study, we specifically applied the upper bound in the context that the noise of different quantitative imaging methods is uncorrelated. In this context, a no-gold standard evaluation technique named regression without truth, in short RWT technique, has shown efficacy. Thus, we are applying the upper bound in the same context as the RWT technique. Now, let us answer the first question. For a certain sized patient population, how best can NGSE technique perform in ranking the methods? In this experiment, we computed the upper bound for different patient numbers. Now, let us first see the results of the upper bound. As we can see that with the patient number increases, the upper bound also increases. To answer the given question, for example, now if you have a patient population that is 65, where you have 65 patients, then the probability for the NGSE technique to yield the correct ranking is around 80%. Then in this case, you are probably good. But if you have a patient population that is only around 25 patients, then in this case, the probability for the NGSE to yield the correct ranking is around 60%. Then in this case, maybe it's better to collect more patient data. As we have mentioned, we applied the upper bound in the context of the same as the RWT technique. So we also ran the RWT technique for 100 noise realizations to compute the experimental performance in yielding correct rankings. As we can see that the efficacy of the RWT technique achieved matched the upper bound, which means the efficacy of the RWT technique achieved the upper bound. Similar results can be observed in correctly identifying the most precise method. Both of these results demonstrate the efficacy of the framework in providing the accuracy of correctly ranking the methods. Now let us answer the second question. For the segmentation methods that has inherently similar noise-to-slope ratio, how accurately can NGSE techniques rank them? In this experiment, we consider 3 sets of segmentation methods where the separation of the NSR values are gradually decreasing. Now let us see the first set of segmentation methods where the true NSR values are very well separated. We can observe the results is very similar as the previous results. Now let us see the second set of segmentation methods where the true NSR values are moderately separated. We can observe that the performance of the NGSE technique in ranking the methods is actually decreased. Both the upper bound and the experimental performance of the RWT technique both observed to be decreased. And if we consider a similar performance like 80% accuracy in correct ranking, we can see that in this case, more patients are needed for the NGSE technique to yield this similar performance as for previous set of segmentation methods. Now let us see the last set of segmentation methods. Again, we observe where the true NSR values are only slightly separated. Again, we observe that the performance of the upper bound and also the experimental performance to be decreased. And if we want again a similar performance, then more patients will be needed. Similar results can be observed for correctly identifying the most precise method. So the upper bound indicates that the performance of the NGSE technique in ranking the methods will decrease when the separation of the true NSR values decreases. And if you want a similar performance in ranking the methods, more patients will be needed for the segmentation methods where the true NSR values are only very slightly separated. Now let us answer the last question. How does no gold standard evaluation comparing to the evaluation with gold standard? So in this experiments, we computed the upper bounds for no gold standard evaluation and also for the evaluation with gold standards. To compare the difference between them in different conditions, we'll again consider 3 sets of segmentation methods where the separations of the true NSR values gradually decreases. Now let us first see the first set of segmentation methods where the true NSR values are very well separated. Now we can observe that both the upper bounds in both cases is gradually approaching the 100% accuracy. And for the patients, for this part of the patient numbers, the difference between these 2 cases is actually decreasing. Now let us consider a scenario that maybe you have only 100 patients. You have 100 patients. Now we can see that in this case, the performance for the no gold standard evaluation incorrectly ranking the methods is at around 90%, and also the difference between no gold standard evaluation and the evaluation with gold standard is actually pretty small. In this case, maybe the gold standard is not helping very much in improving the performance of yielding correct rankings. Thus, we might consider thus it might save us from the time-consuming process of collecting the gold standards data. But if you have only 30 patients, we can see that in this case, the difference between no gold standard evaluation and the evaluation with gold standard is around 12 or 13% in the correct ranking. Thus, in this case, you might consider to collect the gold standard data. Depends on the difficulties of collecting the gold standards data. So we can see that the upper bound is guiding us on the necessaries of collecting the gold standards data. Now let us see the second set of segmentation methods where the true NSR values are moderately separated. We can see that the performance in yielding correctly ranking in both cases both decreased, and the difference between these 2 cases actually increased. Thus, in this case, if you have a very small patient number, for example, less than 200, maybe it's better to have the gold standards data to improve the performance. But we can see that even though in these cases, as the patient number increases, both the no gold standard evaluation will still approach the 100% accuracy. For the last set of segmentation methods where the true NSR values are mildly separated, again the performance in both cases decreased, and the difference between them seems to increase. But still, both cases will finally approach 100% accuracy in correct rankings. Similar results can be observed for correctly identifying the most precise method. So the results indicates that as the patient number increases, the upper bounds for no gold standard evaluation will gradually approach those when gold standards are available, and both of them will approach 100% accuracy. And also we can see that the upper bound can guide us on the necessaries of collecting the gold standards data. Now to answer the question, how accurately can quantitative imaging methods be ranked without ground truth, we derived an upper bound on no gold standard evaluation. The upper bound has multiple applications. It can provide insights on the performance of the NGSE techniques for different patient numbers, for different separations of the true NSR values, and also it can guide us on the necessaries of collecting the gold standard data. And in the context of our study, where the measurement and the true values are linearly related and the noise of different methods are uncorrelated, we observe that the upper bound of no gold standard evaluation can gradually approach that when gold standards are available, and both of them will approach 100% accuracy. Some limitations of this work, we derive this upper bound for unbiased NGSE techniques. Thus, we might want further to expand to the expand the upper bound for biased NGSE techniques, and we might assessing the impact on upper bound when there is model mismatch. And also, since all this studies in this presentation is purely numerical, thus we want to demonstrate the application of the upper bound in clinical settings. And that's all for the presentation. Thank you for listening.